let's see, it's going to take me some time to get to know you. We are not all here. So before Vasif, he's not here. Vasif Ahmed from, we have Helal. Hi. Okay, a little different from the picture. Helal is from Palestine. I'll show you my glasses. Javier? Javier or Alejandro? Javier. Alejandro. That's Alejandro, Guatemala. Okay. Let's see. Jezreel. Did I pronounce it correctly? He's not here yet. Jezreel. But it's correct, you think?
Yes.
Philippines. Then we have Esteban. Esteban from Venezuela. Where from in Venezuela?
Huh?
Where from?
Merida.
Merida. You are from the group of Merida. Okay. I have Ahmed from Egypt. Hazim.
Yes.
Hazim from Sudan. Jose or Jose Guillermo?
Guillermo.
Guillermo. That's Guillermo. Okay. You are from Mexico. Jorge. Jorge. Yes, Jorge is correct. From Ecuador. And we have also Julian. He's not here from Venezuela. My name is Goran, as you know. This slide is not working.
They don't use it because
of the recordings.
Yeah.
You think it's better? I always used it. Okay. Shall we give them a few minutes? You think they're on the bus? You have any idea? Did you see them?
No.
I don't know.
The weather that's scared me? So what did I learn by communicating with you? That basically almost none of you want to do particle physics, okay? There is someone is undecided, I don't remember. I think you told me you were undecided, am I right? No.
I said
No.
that I would like to do particle physics.
Particle physics, no, you actually are interested in particle physics, okay? You were clear. Who else was, remind me?
I'm not doing.
You are undecided.
Yes.
Helal, I pronounce it correctly?
Yes.
Make sure that I pronounce your name correctly, okay? Just correct me if I don't, it takes time. And you told me
Particle physics.
particle physics. Okay. The rest, it seems, either cosmology
Well, I still,
or more formal things, right?
I still don't decide within the time perspective.
You're not sure
I
yet.
like many things in there.
Hello. So who do you see? It's hard to be sure from the picture. Your name is?
Wasif.
You were Wasif, okay, yes, okay. Now it fits. Wasif. Julian, oh, you're Julian from Venezuela. Where from in Venezuela?
Caracas.
Caracas, okay. Yeah, because I know Venezuela, you are then Jezreel, right? Pronounce it correctly?
Jezreel.
Jezreel, okay. Jezreel. And we were just discussing how apparently only a few of you are really interested in particle physics. Okay. The times are changing, it used to be the other way around. Sorry, you...
No, I just said that I am interested in more in neutrinos, which is like cosmology.
No, it's okay.
So my part of neutrino that is also with cosmology, so it's
Okay.
like both.
Okay. Well, the field of so-called astroparticle physics in recent years has took off and became as, if not more dominant than the particle physics in the field of particle physics. The reason being that for a long time we didn't have experiments in particle physics. So it stopped being a particle physics by definition, right? You need experiments to make sure that you speak of physics as natural philosophy. It's the science that studies phenomena of nature. But since we do have a machine now, we have experiments, we have LHC going on, which could uncover a new layers of nature, okay? It's also a moment to rethink. So kind of my mission here is, I take it upon me, to try to convert some of you, to try to show you the beauty of doing particle physics. from the phonology that you learned from Smirnov, going towards more formal, if you wish, structured theory of the same phenomena, basically, okay, in a more modern way. So what it is, it's of course, as you know, the marriage of field theory and the phonology of particle physics. So in order to start the course, we have to sort of chat a bit today. I have to get to know you in a sense to get a feeling of what you know, and you should get a feeling of what we are going to discuss here. So let's see. It's very likely that most of you know actually what the standard model is. So if I ask us in the air like this, what would you tell me? What do you know? Is there anybody that volunteers to tell me something about what the standard model is? It's supposed to be the theory of all the particle physics phenomena, right?
The theory described by the trans product with the SU3.
Okay, so we have SU3, let's start. So what we have to describe, in a sense, it's kind of trivial. We have to describe strong interactions if we are successful, the interactions that keep us together, the particles inside us, right? And they have said that's based on SU3. SU3, how do we call it?
Color.
Color, SU3 color. The next word, what is the magic word? There is a magic word that describes all the
Blue one?
Gauge.
local gauge. Okay, the crux. The word that describes the standard model physics is gauge symmetry. All of them are based on gauge, local gauge transformations. Okay, if I ask you, what is the main aspect of this physically gauge? Okay, maybe keep the question in the air and we just go on. This is what you said, color, called the theory of strong interaction, successful, okay? Then we have SU2 for the weak, and U1 for electromagnetic, okay? So we have weak, and we have electromagnetic interactions. Now, as you know, okay, the thing that you've studied up to now was U1, the theory of the electromagnetic phenomena, QED. So what is this main aspect of the gauge symmetry physically? I don't care about the mathematical aspect, which maybe is one of the most important developments in modern physics at all. If you read Newton's thoughts, when Newton writes his theory of gravitation, the way he writes it, it's a sort of God-given interaction, right? Somehow, I feel you, you feel me, Earth feel the sun, and vice versa. But Newton says it cannot be like that. Anybody who has any deep thought on nature, that's gonna be something that mediates this force. It's very interesting because often it is attributed to Newton, this concept of the instantaneous force, which was wrong. Even at that time, he thought. And we could say that the main progress of physics in general, particle physics especially, is the fact that the forces are mediated by messengers, which is automatically incorporated in the gauge principle. Okay, this is what will be the essence of the model. They somehow go together. If I have messengers, you will see that I get gauge symmetry. Naturally, if I postulate gauge symmetry, I'm forced to have a messenger. And we can say it immediately. What is a gauge symmetry? It simply says that if I have a field, a wave function of some field, which transforms by some global transformation with a change of phase, it becomes gauge if alpha becomes a function of s, right? I've gauged it. So I'm asking that I have the freedom to perform a certain transformation here, and Hellal there can perform his own transformation, and we should somehow have the same theory. But someone has to know this, and to speak to both of us, right? To carry the information, okay? That automatically tells me there's going to be a messenger of the force, and it's better move fast. And how does it work? In order that the theory be covariant, invariant, to be physically well defined, right? If I have derivatives, and I do have derivatives for sure because there is kinetic energy, wherever I see a derivative, I should write a covariant derivative, right? So if there is some interaction, let's call it G. In general, it may not be charged. And it could be that there is some operator that we call charge that measures the strength of that interaction. For example, in case of electromagnetic force, that will be the charge. And then electron will have charge -1 in our units. Up quark we have charge 2/3. And down quark -1/3. I don't want you to know, but we do physics, you and I do physics because we didn't want to remember things, right? The beauty of doing physics is not like studying biology or law or medicine, is that you don't have to remember things. But few things we should. So I'm going to ask you, I'm going to invite you to remember the charges of quarks. And let's say the things that we want you to know in the middle of the night is also Pauli matrices. Let's say there will be few things I'm going to hope that you remember and not have to really rederive every time. Of course, you can do that. So in order to make it invariant, I'm forced to introduce, if I believe in this principle. Well, what comes first, chicken or egg? It's a delicate question, right? Did the principle come first or the first interaction that had the symmetry? Okay, we'll talk about that. But if I believe, if I start with that, I'm forced into this. And then I will see that the theory is invariant, as you know, if A mu transforms, okay? We know this from the times of classical electrodynamics as 1 minus G, or plus or minus the way I wrote. We can check that in due time. Now, before I go on, maybe usually I wait before I say this, but maybe it's important to stress it now, that when you have a symmetry like this, it's any internal symmetry. What follows according to M in ether is the conservation of a current, right? In this case, you remember the current which is conserved? J mu is psi bar gamma mu psi. And in order to count the charges of the particle, we can hide Q inside. Okay. It's conserved without or with Q. So this is the symmetry. The symmetry is something that leads, this is very important, to conservation laws in physics. Okay. Now, gauge symmetry in that sense is not a symmetry, really. There is no new conservation law. Nothing will emerge from here. Actually, it's instead of being this funny thing that does the job that it does, it actually provides the dynamics. It doesn't tell us any more about the symmetry. What it tells us that there has to be someone responsible for the force. It's very different in that sense. And notice that the reason I have this, maybe you know, maybe someone will say it for me. Why is it that I have this freedom? What I'm saying is that M is not a free field. Why? Notice in order for this to be invariant, you see immediately that you cannot write the mass term. Because if you wrote the mass term, let's write here, there will not be such symmetry, let's call it, such local information. I can't write that. This is very important. Now, when I have a mass field, how many degrees of freedom does it have? Because I can't stop the mass field. No? It's a crazy object. It always flies with this velocity c, right? It's strange to understand that such an object can exist. And the degree of freedom elicited, right? The projection of spin in the direction of motion. That is Lorentz invariant. So there will be two elicited, which are plus and minus 1. So it has 2 degrees of freedom, but see, but what we like. We like, since we like Lorentz symmetry. You know, during the course we'll have to rethink about the symmetries which are good. And we believe in necessarily that symmetry may not be good. For all that you and I know, Lorentz symmetry may not be a symmetry, but it's so good. And we are going to assume that it's valid. Maybe at the end of the course, or sometimes towards the end, we can come back. So the reason they introduce mu is to have equivariant way of writing. I will profit from the Lorentz symmetry. That forces me to have 4 degrees of freedom because that's the derivative at 4 degrees of freedom right times the space. So the reason that I have asymmetry is really that they are more counting degrees of freedom. They cannot be physical. If they are not physical, then there will be some constraint. There should be some possibility of eliminating some of the degrees of freedom. So if you say asymmetry, it's just the bookkeeping. If she's telling us, I want you to know from the first day that it's not a symmetry in the usual conventional sense of the word. Just a reflection of the fact that I have to make degrees of freedom. But anyway, now we learn that you all know that the standard model is symmetry. A simple extrapolation, by the way, they develop. It went in this direction. Literally. But imitated as a set of QED with one QED. So what else do you know about the standard model? There is one fundamental property. I'll help you. The Higgs mechanism. What is that? Why do I need the Higgs mechanism? Okay, of course, the Higgs boson now. It's funny to teach today. Because the reason is the Higgs boson, so why am I making big fuss? Right. Right, but if I believe in the gauge principle, then photons will be massless. People often say that the reason the photon is massless is because of the gauge principle. You think it's a good argument?
It's because of experiment.
Well, experiment never gives you 0. So why do I, okay, well I like that you said because of experiment. There should be a guiding principle after all. Physics is about studying natural phenomena. So why do we believe experimentally that photon is massless? That means there is an upper limit of photon mass. And that number is small, right, usually. Usually when you don't know something, you and I, what we say, if they ask us, well, how small, you say, very small. Let me ask you if you know what is the experimental limit on photon mass. It's just been improving over the years.
10 to the minus 14 eV.
Actually, particle data group puts it 10 to the minus 18 now. And I just checked it accidentally last night. When I'm thinking about the things that I've been talking about today, rechecking, rethinking about what I want to say today, that it's 10 to the minus 18 electron volts. Now, why is this very small? Because this is 18 orders of magnitude smaller than the masses we know, which are neutrino mass. Neutrino mass is order of electron volt. These are few numbers that would be nice that you remember, okay? Or if you wish, okay, this is about 10 to the minus 18 neutrino mass, or if you wish, 10 to the minus 24 electron masses, okay? So this is an extremely small number, so it's natural that you and I, for the rest of this course, will assume that photon is massless. But this is not because of the gauge principle. Because if I believe in gauge principle, then I will also tell you that the messengers of ink interactions are also massless. But they're not massless. So what do I do if you tell me that a particle has a mass? I break the gauge principle. And I do it in an elegant manner, okay, that Higgs and others taught us. This is what Higgs mechanism is all about. Higgs mechanism that we will have to study here. An added feature of the standard model is a way of giving gauge boson masses without sort of giving them mass. It's a strange thing. It's in 1960. It's sort of nice to sometimes to go through the source of the revolutionary ideas, because in the beginning they are very confusing, very obscure. Not only people that listen to them have no idea what is going on. Usually the authors of these ideas don't know what is going on. It took 3 years to Dirac to say, okay, there is a positron. Remember, Dirac equation tells you immediately there is a positron. But he's going to take 3 years to get courage to say it, okay? He's confused as hell. He even says at some point that proton could be maybe the anti-electron. Well, they ask him, he has 2,000 times bigger mass. Okay, we'll understand that one day, Dirac says. This is how the ideas do not develop the way they are done in the books, with this simplified clarity. So Nambu in 1960, most of these years won't tell you anything, at your age, okay? I'm reciting them. They talk to me, they don't talk to you. Nambu in 1960 gets an idea of so-called spontaneous symmetry breaking. This will be a new way of understanding breakdown of symmetry. So if you look at the original talk he gives in a Rochester conference in 1960, when he finishes, Xin Yang, whose name you know from, a great physicist, right? Who a few years before, in 1956, repeatedly suggests that parity is broken. Li and Yang. A very skeptical man of very strong opinions. Xi and Yang, we were almost colleagues. I used to work at Brookhaven. He was at Stony Brook, and I couldn't understand why he would treat Nambu the way he treated. He asked Nambu, if I understand, he says, you're telling me that the symmetry is broken in your theory. Yes, Nambu says, you got it. But if I understand well, you're also saying that the symmetry is not broken. Yes. I says, let me explain to you. This cannot be. You see, this is the basics of logic. Either something is there or it's not. So let's try again. And then 3 times they go through this song and dance. Do you think the symmetry is broken? Yes, says Nambu. But you say it's not broken? Yes. Well, that's the crux of the Higgs mechanism. It's based on spontaneous symmetry breaking. I'm just giving you the idea, the picture of what we are going to be discussing in the course. You can relax at this point. This is all going to be done very, very carefully structured in a disciplined manner. Spontaneous symmetry breaking. It's so subtle that one of the main, if you wish, divulgators, Sidney Coleman, who used to write beautiful, will mention there are actually books on his lectures. And from time to time I'll recommend them. He used to say that this is a terrible name, we should call this a hidden symmetry, because the symmetry is there, as always thinking that it's not, depends how you look at it. So this funny logic of saying something is either or not, as you know, electron is a wave, but electron also is a particle. Okay, we have to think about a situation where there is a duality of apparently different ways of understanding the same phenomenon. So you see, the standard model that we'll be focused on, a gauge theory of weak and electromagnetic interactions later, strong, will require us to learn the Higgs mechanism. I have to spend some time on that. It's such a way of breaking the symmetry. So it's interesting, it started as a theory of interactions. It became a theory of mass. What we will learn here that there is a unique manner in which all the elementary particles of the standard model gain the mass. The Higgs mechanism. Now, a little bit of group theory. When I have a one theory, how many gauge bosons do I have? How many messengers? One. One generator, which I call Q, one gauge boson, okay? So here number is, okay, messengers. We'll have one here. Here? Three. What are they? W plus, W minus. And of course the new heavy neutral gauge boson, right? They were discovered long ago. And here, what is the magic number here? 8. And they're called gluons. There are 8 of them. In a similar manner, not by direct experiment, okay, we have to talk. This is a very strange theory because these particles that we describe by strong interaction, they are quarks and gluons. We never see them really in a sense of isolating them in a laboratory, right? What the strong interactions describe is this sort of funny object that I draw spherically, proton and neutron, right? The nuclei that apparently are made out of quarks. I say apparently, right, because we don't isolate them. We now believe very strongly, although there is no formal analytical proof, that these particles, quarks and gluons, are confined. So for example, proton will be made out of 2 up quarks. So if you get the charges, just remember 2 up quarks and 1 down quarks, and they will give you the number. They have to sum to 1, which is our convention, the charge of the proton. The same convention according to which the charge of the electron is -1. Just a normalization. Often you read that there are fractional charges. There are no fractional charges. This is just a normalization, right? All the charges are integers. All of them. If I normalize to the smallest charge in nature, which is a down quark. Right? If we had seen the down quark first, we would have called that charge 1, and then proton would have the charge 3 times bigger with the opposite side. In our units, Q up is 2/3. But don't be fooled. Appearances may be deceptive. These are just a funny way of choosing a unit. Notice that they are all integers. 3 times down quark, -3 times down quark, twice, -twice down quark. There are resonances that you know that we kept discovering, particles like delta plus, which have charge 2. Okay. By the way, this is an amazing miracle. Right? Imagine that we find that in this room, all of us have a mass, which is an integer of the lightest, let me guess, maybe she's real, I don't know. Whose light is there? Some of you who are skinny, okay. That would be amazing, right? Because the things we are familiar with is the continuity of physical parameters. It's a profound, deep mystery. The charges are quantized. We say, can you think of some explanation, or maybe you heard of some explanation how charges could be quantized? Did you ever read, come across? It has been a long time. There has been maybe a central fundamental issue of modern physics.
Dirac tried to quantize by using the system of monopoles, I think.
These are side comments, okay? There will be digressions. Today's lecture is most of the side comments. Let's say we start, maybe we start a little bit today, but probably on Wednesday. People used to dream about the symmetry between electric and magnetic phenomena. There is a profound symmetry between electric and magnetic field, right? You can generate one by dynamical changes in the other and so on, with one profound difference. There are electric charges, but we have never seen a magnetic charge. Remember, as a little kid, I was driven crazy by an older brother who was trying to explain them. The magnet, you can't break it. They always have these two poles, but how can it be? Why in the world should you have always two poles? So people used to think about that. The world would be nicer if you had magnetic poles. It would be more symmetric. You know, the guiding principle of symmetry has led to often revolutions of physics. So one guy that took it seriously, as you tell us, is that Dirac says, okay, let me really take it seriously. Maybe in electromagnetism there exists also a magnetic pole. If there is a magnetic pole, I have to write a quantum theory of magnetic poles. And that's highly non-trivial. It's one of the most beautiful papers ever written in physics, okay? I would say even more beautiful than the Dirac equation, which is an embodiment of a beauty, right? It leads to rich physics. What he shows, by asking the quantum mechanically consistent theory of magnetic monopoles. And it's funny, it's enough that there is one magnetic monopole. Imagine one only. You would prove that the product of electric charge times the product of magnetic charge has to be an integer. One monopole would suffice. In 1982, in Stanford, Cabrera was seeing, actually it was 14th of February, he was somehow getting in the apparatus what seemed to have been a monopole passing through his plates. We can talk about it one day if there is interest. So the joke at that time, monopoles were never found, they were looked for desperately in a systematic way. There has been an ongoing experiment in a Gran Sasso laboratory in the Italian Apennine Mountains above Rome, about 140 kilometers, above the town of L'Aquila. They became famous some years ago due to the devastating earthquake. Some of you may have read about it. They've been looking for years for magnetic monopoles with a detector which is as large as a soccer field, you know, hitting upon the... None were found. So the joke was that there is only one monopole in the universe, and he passed the days through his plates and is now freely wandering around the universe, right? But you can imagine that many people are excited about the possibility of magnetic monopole, because this incredible miracle would be explained naturally. What could be another way you could think of arriving at quantization? Can you tell me if some quantum numbers you know is quantized?
Body number?
I'm not sure. You see, I have to, in order to be sure, I have to attach a barrier number to the, I can do that to the quarks, but I have not really seen quarks. Okay, there is something more elementary that I'm sure about and you are sure about. It's been tested very well, which is quantized. You use it every day. Spin. And how does it come out to be quantized? Do you remember why it's quantized spin? What is it described by spin?
Commutation.
Right, by SU2 symmetry. Precise. Okay. This is when I say when I wrote you a message, I said you have to know group theory. What I mean, you have to know SU2. And it's not funny because I learn every year that even when people come with a deep knowledge of profound aspects of group theory, they are often not mastering the spin half. So we'll check up on that and make sure when you walk out of here, at least spin half, you know, in your, which you may think you know, and I hope you do. And here what we know is that commutation relations, they define the symmetry group, guarantee the quantized values of spin, right? So we speak of spin half, 1, 3 half, and so on. So you see, one simple way of having charge quantized would be if instead of U1, we had SU2. Because then, by definition, whatever is inside would have to be quantized, okay? We'll come back to that. I'm not going to be focused so much on that, in spite of that being a fundamental question, the quantization of charge. But from time to time, I'm going to wet your mouth and bring some of these fundamental issues, so that sort of we set the stage of what could be the physics we understand about. And this is the reason that I won't start, you know, the way, since you all know this, you should tell me, say, why the hell are you giving this big introduction? Why don't you start writing the SU2 cross U1 gauge theory? We know the gauge principle and see the consequences. I'm not going to do that. I'm going to bug you with history a little bit. I want to show you how actually it was forced upon us. By believing in the gauge principle, I want to show you how at every point, in a very unusual manner, the standard model was a great success of theory beating the experiment. All of it came from the theory. And I think it's good to see this evolution and to see how from darkness the light emerged, giving us an idea of next. We may be wrong, right, when we look at the past. But when some things work, it's good to see how it came up to be on us. So what I'm going to do, I won't talk for the time being about strong interactions. It's too complicated. Too serious of a subject. We have to understand what I mean by actually the strong force, especially since the particles in you and I see are pions and protons and neutrons, not these guys. Okay, even the language is sort of strange that I'm using when I speak of quarks in terms of the strong interaction. By the way, before I erase SU3, can you remind me why we believe that quarks exist, since I don't see them apparently? Or how do I see them? In some sense I see them if I talk about them.
Because scattering experiments,
Right.
the particles scatter like one.
Right, in other words, okay, so let's say, just a few words. If I hit the proton with a fast electron, for example, neutrino or electron, whatever I want, when I hit it, I see that it behaves as if it's made out of this. And it's very funny, in the beginning, and especially the higher the energy I have in my hand, the more proton behaves as if it is made out of the almost free quarks. It took some time to learn actually that what we see also are these exchanges of, you know, the gluons that are here. Something is providing this confinement, right? I don't want it is some kind of string people used to imagine, you know, you naively, or maybe there is something happening there that I have strings that I can't break, or actually I cannot separate. When I try to separate, it breaks. Something happens, prevents the particles to going far to infinity. So that they, you know, like if you have a tightly closed shopping bag, doesn't matter what's inside, it won't come out, okay? But when I go to very high energy, and in here, how do I define the high energy? Remember, the mesh of full numbers are never big or small. It has to be compared to with the mass scale in this question. In question, proton mass. That's a natural scale of strong interaction. It's the only scale at this point. So when I say very highly energetic particle, I mean much bigger kinetic energy than the mass of the proton. The bigger the energy, the more the quarks look free. In other words, when I scatter it, proton behaves as if it is made. I don't really see them, I didn't isolate them. Which is very strange. I speak of a strong force. But when I do this experiment at high energy, the force is not strong. It's almost not there. And this is the concept that you may have studied already, or you will learn before the end of the course. Who is teaching the course? Saif is teaching the field theory course. And Saif is going to teach you, if you didn't do yet, that the interactions, the forces, the so-called Catholic constants, are not really constant. They depend on energy. Fortunately. That saves us, okay? Because I can describe QCD as a very successful theory if I go to higher energy. Okay? Then by extrapolation, I hope that when I lower the energy, I get a reasonable picture of proton, neutron, and ions. Okay? Where the theory has been tested with a great precision is at high energies. And there is an art of studying it at low energies, and we talk about it later. But we can really believe today, as unlike, you know, one of the fathers, who were the fathers of quarks? Anyway, let me see. Typically, everybody only remembers Gell-Mann, although Gell-Mann didn't take them so seriously. In 1964, you will notice a magic era of 50s and 60s. It's all happening at that time. It's impressive. And Zweig. Gell-Mann, a famous professor at Caltech at the time, Zweig, a graduate student. Zweig takes them seriously. We spend the next 3 or 4 years developing the theory of these quarks. If you read Gell-Mann's paper, it looks almost that he is sure they are just mathematical objects, useful to classify, you know, the octets of mesons and baryons. By the way, we often talk, when people describe the history of science, they talk of Nobel Prizes, a great physicist, okay? What I like to talk about prizes which are not given. One of the craziest aspects of modern particle physics, the father of quarks never got a Nobel Prize. But Kobayashi Vaskawa, just by suggesting fifth and sixth quarks, got a Nobel Prize. Amazing. I hope that somehow before he dies, he's coming almost 80 now, or maybe no, easily 80. That this will be correct. It is said, let me come back to strong interactions later. Especially because in order to discuss strong interaction, I need you even more knowledge of field theory. You know, when I start the particle, the standard model course, there is always a dilemma when to start. If I start early, we can do it in a more relaxed manner. We have maybe 2 lectures a week, not 3. You know, it's a heavy course in some sense. There's a lot to learn. But then you have almost no knowledge of field theory. Ideally, I should start in May. There is no time, you know, so there is this compromise. Okay. So hopefully there will be some more knowledge about the energy dependence of coupling so that we can attack this more seriously. For the time being, let's focus on the electroweak theory, we call the theory of electric and magnetic and weak phenomena. And we said what we have to learn is the Higgs mechanism implemented in the gauge principle. Okay, but let's try to see why we are here today. How it all. So in order to do that, let me see what you know about weak interactions. I'd like you to see somehow that although it was highly profound what the fathers of the Standard Model did, it was also reasonably natural. You see, let's go back to late 50s, mid 50s. By that time, the QED is worked out by Feynman, Schwinger, Tomonaga, Dyson's crowning achievement. In the end, what is emerging is information about the weak interactions, okay? The theory of weak interactions, as you know, was the effective theory was postulated by Fermi in, let me see if you have an idea of time.
30s.
30s, very good. 1934, I believe. There's always a little, you know, I could be wrong by a year. Fermi says, just by imitating the effective theory of electromagnetism, what is the electric theory of electromagnetism? If I write effective theory of electromagnetism, it's going to be a product of electromagnetic currents. And it's out if you were big in the energies or momenta of the order Q, there will be 1 over Q squared. Okay. This will be the effective Hamiltonian he knew at the time that would describe electromagnetic interaction. In the modern language, how does this come about? How do I get this Q squared?
Dimensional analysis.
Dimension analysis, excellent. This is dimension 6. Okay. Okay. One very good argument. I have the electromagnetic current, E phi bar, gamma mu psi. By the way, I should put E squared here, the strength of the charge. So I took the Q, this number, plus or minus 1. The fields carry dimensions, as you know,
Yes.
in the units of mass. As everybody else, I'm going to be using natural units, right? These crazy units in which H bar is equal to C is 1. So what is the unit of
3 by 2. 3 by 2.
3/2? How would you know that?
From the kinetic term.
From the kinetic term. If you have questions with the things said today, stop me. If you're shy to stop me, and I hope you won't be, okay? I cherish, I really need questions to know which level to teach you. Please make sure that then you go and this afternoon you don't fall behind. You don't wanna it happens that I lose you today. I don't want to lose you on Wednesday, but not today. Okay? The things that I say, please stop me. We are just sort of chatting, okay? So this would have dimension 6, right? But the Hamiltonian or a Lagrangian, whoever written effective Lagrangian is the same thing. This is a interaction. Must have dimension 4 in the units of mass, right? Because action has no units. Why don't I write in the terms of Lagrangian? Action we know, which is d4x times the Lagrangian, has no units in my units, so that this has a dimension, inverse dimension length of mass. I forgot. Excuse me. For some reason, I forgot. And how do I know that this is inverse? The unit of length is inverse of mass? From uncertainty relations, for example. Okay. Well, there are many ways of looking at it. But just from PQ distance or PX equal 1 I, whatever, 1 is a unit, I will learn that this has inner dimension. Momentum, which has with velocity equal 1 unit. So I know that the dimension of Lagrangian in the unit of mass is 4. The unit is mass. This is how you told me from kinetic energy. You will know that then by writing today nothing is written in a organized manner from this term. I will know the dimension of size 3.5. Okay, I'm reminding you here quickly. These are just telegraphic reviews. So there could be dimension analysis, or anyway, help me. You've learned how to derive a propagator, at least for a scalar field?
Yeah.
Okay.
Yes.
Did you do the photon? Good. Yes or no? You're there. Yes. Okay, so the scalar propagator, okay, in telegraphic, disorganized manner. Don't worry if you don't catch any of the notes today. I will start on Wednesday, and whatever I said today will be done carefully. So for example, the scalar, what we call a Feynman propagator, would be in momentum space. Would be. There is an I, okay, in its c squared
minus n squared.
minus n squared, and the d mu nu, say Feynman, okay, so this is scalar. This is the, someone reminds me? Well, it depends on the gauge.
Yes.
That's the other problem. There's an interesting thing that there is a minus I here. I don't know if you remember why. And then there is g mu nu. And then a function which is a function of the gauge fixing term that you're going to go through in the homework, which may be just rewriting what you did before, k mu, p mu over p squared. This is the photon propagator, okay? So different people will use different gauges, okay? When I throw this away, this is called Feynman gauge. Why doesn't this matter? How do you know immediately that this cannot matter without even doing profound calculations? Okay, let's do that. Why is it that I can't remember? Hour and 15 minutes or hour and a half? What are? Hour and a half or hour and 15 minutes? Hour and a half. Very good. Okay. I need a half an hour just to have sort of to bring you to where I want to start. And the things I struggle a lot when I teach, and I'm never happy, is how to make sure that you people have fun, that you're not caught in some technical details. Of course, some of you just like technical details, and that's why I want to do formalism. So maybe then again, it's not even a good argument. But this interplay, you know, making sure that you get a sense of physical ideas, the touch for doing physics, okay, in case you want to do particle physics. And of course, the struggle and the rigor of doing boring calculation in which every sign and every factor of half, as you know, is essential, because otherwise everything goes wrong. You can imagine as I see what a factor of 2 would do. And we have to make sure that these guys produce what they produce. How would I then, without using the dimension analysis that Vasif suggested, how would I do it? How would I arrive at this from a modern point of view in which there is a messenger of the force, right? Because the interaction is not that, the basic interaction, so how would I call it? The fundamental interaction, let's say, as you know, is here would be I, psi bar, gamma mu, psi, a mu. So, and this is E, J mu, A mu, electromagnetic. So this interaction, the way I will produce it, okay, I will have okay, let's do the Feynman way of doing it, which is maybe the really plot the psi bar psi. So psi entering, psi bar coming out, okay. There is at every vertex there is E gamma mu, psi psi bar, E gamma nu, and then I just exchange the photon, which means writing the propagator, right? And here I have that function that I wrote there. How do I know that this will not matter? Because that's one of the things we have to worry about a lot, the gauge invariance, and it becomes more non-trivial when you do the non-abelian theories. This, you know, abelian, a language introduced today, is U1. Non-abelian is anything bigger than U1, okay? And of course, we have to learn non-abelian. You see, here there will be two terms. In other words, I will have psi bar, gamma mu psi. Let's write it. So I have a propagator which...
Because it's massless.
G mu nu. Sorry?
Because it's massless.
No. Well, in some indirect way, yes, but not directly. I don't even have to worry about the mass. Sorry, why did I write m squared here? I'm sorry. Well, you know that in QED there are infrared divergences. There are divergences that hit you when you have very, very small energies. Okay, they're very interesting. Okay, I don't know whether you will learn anything. The way Feynman used to get rid of them, for example, he used to work with a small photon mass, and at the end of the day, he would take the mass equal to 0. Now, that sounds crazy. There are two things that sound crazy. First, that it does not matter. It seems to matter. And that this does not matter because a massless field has 2 degrees of freedom. You knew that, helicity. What about the massive field? How many degrees of freedom it's going to have? Why? Because I'm going to stop the and I'm going to ask someone to measure the spin. I don't know how to do that, but someone is going to do that for me, and I know that he has 3 degrees of freedom because the spin is 1. I know that from the Lorentz form. We'll do that. So when I put the mass here, I have 3 degrees of freedom. When I take the m going to 0, I have 2 degrees of freedom, okay? And the answer is hidden here, because you will learn, this will start on Wednesday, that with 3 degrees of freedom, you get this, what we call longitudinal modes in the direction of the propagation, p mu, but they do not matter in QED. It's here. K square, I wrote here. Psi bar gamma nu psi. Oh, I'm sorry. It's a reminder for something I have to do. Maybe you see, I call it Q squared. Why don't I write it Q squared the way I did? I'm sorry. Let me call this momentum here. I apologize. Just that I call it Q squared. That would be the, in this case, this momentum Q is the exchange momentum, right? The momentum I would call here K1, K2, K3, whatever. Exchange momentum I call Q from the beginning, so let me keep it here. The first term immediately produces, you agree? It checks out the dimensional argument, okay? What about this? Notice what it does. It does psi bar, and what is Q? Let's be careful here. And enters the particle with the momentum K1 and goes out the particle momentum K2. So psi bar of K1, gamma mu, psi of K2, then notice there will be K mu here, this piece. You agree? There will be F of C. Let me write it a bit more. This first term, psi, remember the first term I called J mu J mu 1 over Q squared. You agree? This is the first term, by definition, because of J mu. There was E. At every vertex there was E, so there was E here and there was E here, so I'll get E squared. Minus. The second term, there will be also E squared over Q squared. Psi bar K1, K mu, gamma mu K mu, Q mu, K2, and so on. I'm just writing one piece. Okay? There is also, no, why don't I write? Psi bar K3 maybe, I call this K3. Entering here, I call this K4. Psi bar K4. This I call K2, I'm sorry, this is K2. This is K1. K4, gamma nu, Q nu, psi of K3. And then there is one more 1 over Q squared. Okay, that would be the second piece, okay? I didn't have to write it in such a boring detail. Okay, notice this. This is psi bar of K2, gamma mu. And what is Q? It's, let's take it here. It's K1 minus K2. So I will write it K2 minus K1 mu psi of K1 with a minus sign. So I have, this is minus psi bar gamma mu. Well, I don't have to write. Do you notice or not? It's called Dirac equation. I'll even remind you of the Dirac Lagrange as I go along. We'll be systematic about everything, okay? But just to, what is the Dirac equation? It's normally written as P slash minus n, psi equals 0. Which means when you have, look for example the second piece is even more clear, but they're equally clear. You have psi bar, so the typical term here is psi bar gamma mu K1 mu psi of K1 when I'm here. According to Dirac, P slash, which is P mu gamma mu psi, is equal m psi. So this piece is going to give me m. But this piece may also give me m. Please check. So it cancels. When you talk of physical particles, we call them on shell, remember? I'm talking about here the physical process of some scattering of fermions that give me current interaction, okay? These particles are physical particles, unlike the guy that is propagating, okay? This guy can live everywhere. Q is not on a mass shell. Actually, I have to worry when it's on mass shell. I have to think about that, okay? There is this finite psi epsilon prescription that Sage must have talked about. And this is why the longitudinal degrees of freeness do not matter. I can forget about them. And that, of course, that's why most people actually did that the way Feynman did. He simply didn't write it. Landau used to keep it. But in the end, he used to get the same result, obviously. Why? Because he couldn't contribute physically. Okay. So I will forget it. And so the modern picture, but independently of the modern picture, there was a good argument that you use, which I like. The dimensional argument told me that it has to this form. So Fermi says if I imitate that and I write the same effective interaction for weak interactions, it will be some current that I call weak current, and it may look like electromagnetic, it may not look like electromagnetic, okay? So let me just write it weak here. And it's not going to be 1 over q squared because it's much weaker. In those days, people used to do experiments at the energies which are below electron mass, below even 1 MeV. Okay, we'll have to define the notion of high energy physics is a very interesting thing, you know. Those of us that sometimes work on grand unification, not to speak of people that work on strings, they call low energies this energies of LHC, which is thousands of GeV, because it's low energies compared to the scale up there, which is a Planck scale. Okay, so I have to be careful when I use this language, and I hope that from the context it will be clear. Here, low energy, which will persist up to the 50s, is Q roughly of the order MeV, or below. Weak interactions are much weaker. By dimension of magnitudes, there has to be 1 over some. They didn't see energy dependence, okay, so they wrote to 1 over m squared, which was written in this G Fermi way. There is often here a square root of 2, well, it depends how you normalize your current, but it's typically there. And this number, can someone cite it for me? I know that we don't like to remember things.
10 to the minus 5.
10 to the minus 5, very good. It's about 10 to the minus 5 GeV to the minus 2. I could have written it as sum over m Fermi squared, just introduce some number. M Fermi would be around 300 GeV. You agree? It was extremely big. Crazily big. Weak interaction. If I do experiments at that energies, I will conclude that weak interaction over electromagnetic interaction is simply Q squared over m Fermi squared. I can put GF, okay. I will often introduce this m Fermi to remind you that there is also physical scale corresponding to these artificial dimensionful numbers that don't mean much. For example, we don't like to talk about Newton constant particle physicists, as you know. We like to call about the mass scale, which we call Planck, which is big, very big. Do you know how big?
38.
10 to 19.
The scale. 38 is something else. That would be G Newton in my units, okay. 10 to the 18, 10 to the 19, depending how you precisely define it, okay. You see, I could put a factor of 2 here, depending how I feel on a particular day, or some factor of pi. You know, some people like pies. You know, pi, you have to put a pi, you know, particle physics. You can guess the results by putting a pi somewhere, okay. So it's about 10 to the 18, 10 to the 19 degrees. This is the reason, by the way, that you and I, if we are serious, should not speak of gravity as a particle force. It's irrelevant. Where a side remark again, but very important. Well, let me finish here. So what would I get? This would be MeV, which is about 10 to the 3, roughly 10 to the minus 3 GeV squared, divided by 10 to the 5, right? GeV squared. Correct. So what do I get? About 10 to the minus 11. Am I right? 6 plus 5 is 11. I think that's reasonable. And this is not the cross section I'm talking about. This is just the strength of the effective interaction. If I want to compute a cross section, it's going to be a square of this. So I'm going to learn that the weak interactions are 20 orders of magnitude smaller than the. By the way, they emerged, the theory, just a few years after Pauli suggested there could be a neutrino. We are doing this brief history that will take us another 10, 15 minutes. Why did Pauli suggest neutrino?
For the continuous spectrum of energy and momentum.
There was energy sort of strangely behaving, you know. At that time there were people, you know, there are always courageous people. It's interesting, you know, how you can think of physics in different manners. Bohr suggested, well, let's give up energy conservation, okay. That's opening a Pandora box. You give up energy conservation. This is why I don't want to break Lorentz symmetries. I have friends that break Lorentz symmetries. I wouldn't never do that. You know, I need to have my feet on the ground. There are people who need feet more on the ground. They will never speak of grand unification. They want to do standard models because, as we've seen, you know, it's a question of personal taste. So Pauli says maybe there will be, we call it anti-neutrino. We can remind you later why. Why? I can ask you now.
Lepton number.
Lepton number. We've never seen this breaking of lepton number. We give a lepton number to neutrino. It's a brother and sister of an electron, okay, and this number should be 0 because it's 0 here. We have not yet seen the breaking, okay. We'll have to talk about it towards the end of the course. This fit very well with the massless neutrino. Once neutrino gets a mass, and we know it's massive, we have to rethink. But 1930, Pauli suggests these things apologetically. He writes a postcard, doesn't even write a paper. You know, it's interesting how conservative they were. Dirac takes 3 years to say there is a new particle. Pauli writes a postcard suggesting a particle. Used to be an interesting era. Your reputation depended on what you said. Not today. As I speak now, right now, someone is sending a paper to the archive in which there is a new model with 17 new particles, 5 new symmetries, and so on. Okay. But I was not that conservative, but sometimes I get a nostalgia. That's too much today for me. This was also too much, that you had to be so scared. You know, you should write a paper on that. Fortunately, he was Pauli, otherwise you may lose credit for one of the most revolutionary suggestions in particle physics. New fundamental particles are so rare, especially at the time. And this is our best window. I will try to convince you in the end of the course to new physics. Why? Because this crazy autistic guy has only weak interaction. It's completely crazy. You know? It's like a person that never smiles, never talks, never reacts to anything. You don't know. Just goes through you. You know how crazy they are, right? As I speak now, there are 10 billions of them every second passing through centimeter square of my body. To give you an idea, because the weak interaction is so weak, what is the mean free path of a neutrino? You know, the distance that it goes without hitting anybody. Yeah, well, I don't know. I know it in centimeters. People laugh at me. All units I know in centimeters, which is a bit crazy, right? Cosmologist, of course. It's about 10 to the 18, 10 to the 19 centimeters, roughly. No, look at me, you know, I can go, what, in this distance, half a meter, here half a meter, here maybe a meter, right, here 3 meters, okay, electron much less. Not even a centimeter. This guy practically doesn't interact with nobody. This is what they call weak interactions, weak. That was a fair name. So, this is what Fermi does. This is 1934. Fermi knows I have to mention this joke. Pauli had a very dry sense of humor. He's famous for his criticism, and for his sort of jokes en passant. So, you know, there are a bunch of his students, postdocs. You know, young people, when they are good and they are about to become famous, they are often people, you know, it's natural to happen to you, become obnoxious a little bit, you know. So they're reading a paper of Einstein and they are saying, no, it's not good, you know, there is some stupid paper Einstein wrote. Wait, says Pauli, Einstein is not completely stupid. So you see, Fermi, for example, was not completely stupid. I've mentioned people that were not completely stupid. So Fermi knew there could be a messenger, like a photon. He's deeply aware of that. But you see, the interaction is so weak. In other words, Fermi knows how is the weak interaction. I want to describe here this process. So the current here, what does it have to do? It has to change a proton into a neutron. By the way, in the model language, what happens here is what language?
Downward goes to upward.
Yes.
runs into up quarks. Because neutron, I didn't even write it down, was 2 down quarks. This is 2 up quarks. So if I write in terms of down quarks, the current would be up, out. Well, gamma mu here may not be just gamma mu, okay? So let's be careful, okay? Let's imitate just the down quark. This current, as opposed to electromagnetic, carries charge. If I believe that there is a messenger, I see immediately it has to have a charge +1. Minus a third, minus 2/3. I can put subcoupling constant G here. Or I can put it in the interaction, sorry, this is J mu, so the interaction would be okay, sorry. This is what I meant. This is how the weak interaction would look like. I could have done this immediately. What would I learn? How would the same process look like in terms of a messenger? Well, down quark would become an up quark, would emit a, what is it going? This is in which direction? This is W minus, I guess, going here. Or W plus entering. If W plus is entering, W minus, remember what you know about Feynman diagrams. Particle equivalent to atom particle going in this direction. And I can see from charges, so W minus moving here. If W minus moving here, it's producing an electron continuously. And I have a situation that neutrino is entering, which is equivalent to anti-neutrino going out. This is what Feynman rules are all about. This is what you're learning now. And then I would have the analogy completely by the electromagnetic interactions, if I know the propagator, which is your homework. I define the propagator here. There are very different ways of defining a propagator. They are equivalent as an inverse of the quadratic form. Did you think a little bit about it? If you have any problem, let me know. Today would be good that you ask how to derive it. I gave you Lagrangian, so you have to take the inverse of the quadratic form. It turns out that the propagator is, there is this I. Now it's k squared minus mw squared, obviously, g mu nu. There is no more gauge fixing factor. This is a physical particle with spin 1. There is no gauge symmetry. I broke it when I said the W had a mass. And here what happens is k mu. Sometimes you write k or q or whatever. You should not confuse. Over mw squared. Right. I don't remember if I mentioned in the problem or just told you to derive it. This is what you should get. Again, the first piece, notice. Now, what is the characteristics of the process? When I put here an exchange momentum q, and I'm interested in the energy is q for me and back lost in the past. Okay, 70, 80 years ago. More. 30s, anyway, 50s. 60, 70 years ago. I'm talking about very small. Here, Q is much, much smaller than MW. So if K is much smaller than MW, how does the propagator look like? It's 1 over MW squared. See, MW is sort of similar to that Fermi scale that introduced. The number is a little different because we put a gauge coupling constant. So in this process, I will have a gauge coupling constant G. You know, what I'm saying is that 1 over M Fermi squared, some funny scale that introduced, is actually G squared. And there could be some factor of 2, please. This is over MW squared. You know what the W mass is? Roughly? 80. Even if you know it, it's order 100, it's good for me. So it's a little smaller than 300 because G is smaller than 1. And there is some factor there in the thing, okay? So I can get weak interactions by the analogy, the complete analogy with the electromagnetism, if I take it one step further, Fermi didn't do that. Fermi said, well, how I'm going to look for the particle? Look, that particle will have a mass about 300 GeV. I'm doing experiments at MeV. So I want you to know that he was not completely stupid, and people will think of this as the time went on, but until they could imagine a way of probing that, at that time, when physics was taken seriously as a natural philosophy, people were shying away of seriously pursuing that, okay? Now, if you just wait for experiment, then may be too late. If you speculate too much, you have no feet on the ground. So the art of doing physics in a deep manner is to find that common sense between, you see, not publishing and missing it and not being over speculative. And I can wait for the energies of 100 that came. Do you know when it came? When was W found, roughly?
70s.
Actually, it's 80s. It's 83 or something when the experiment at CERN, Rubia, Durula, and others find a W, okay? But what will change in the early 60s, and this is where the course will start on Wednesday, is an important principle that I want us to follow. Even if I don't have the energy to probe something, if I have a well-defined theory of the behavior of such messengers, it makes sense to pursue it. We'll try to argue. Not just by putting W by hand. Okay. What you and I want to do is somehow what Glashow did. Okay, the story is this is how Glashow introduced the standard model in 1961. So, okay, is to develop a theory based on the gauge principle, according to which W had to exist and its properties were well defined. And moreover, Z had to exist, and that was very exciting. Okay. There was no trace of Z at that time. So I'm about to stop. I just want you to help me in the next 2-3 minutes to establish the, so that I can start being focused on structure next time. What else do you know of weak interactions that I have to worry about? I'm going to take seriously this possibility that there is a W boson, not because that Rubia found it and the guys, but because I want to show you that it's a natural road to take that will lead to exciting physics.
Parity violation.
Parity violation, beautiful, it's okay. The things I will have to worry about. By the way, it's worth saying it here. If this picture is correct, this is what is revolutionary. For large K, weak interactions are not weak. Go to very large K, go to the opposite situation, K much bigger than MW. Now it suddenly looks like a photon. Except, notice this. Something to think about. You and I will have to worry a lot about this. If I get to very large K, I can say it as well today. It's like taking MW to 0, it's equivalent. Well, that's exploding. That's somehow crazy. So the weak interactions not only will become not weak, but like electromagnetic, because if there is no MW, 1 over K squared is the same as the 1 over Q squared that we wrote for the photon. They will become much, much stronger. I have no way of dealing with that. They will become infinitely strong if I go to infinitely higher energies. Okay? So I got to worry about that. The piece here, correcting the relative, to the photon. There is 1 over K squared here, relative to the photon. Okay, so what we have to do, and that's going to take a number of weeks. We're talking at least a month here before I mention strong interactions. I'm going to forget about them, as if they don't exist. I have to develop this theory, and I have to develop a mechanism of understanding the following. The first thing that I've learned, they are short-range weak interactions. But that's no problem. This is equivalent that saying that MW is non-zero and it's roughly 100 GeV. No problem. A massive particle gives me a short range force. because it's so heavy it can propagate. Okay. Again, important thing, there is parity violation, and parity violation is maximum. That I hope you remember. How did they see it? Just a few more minutes. How did they see parity violation? Someone remembers? What did they do? The neutron decays, actually nucleus decays, but let's think of a neutron if you wish. What you have to do, it's at rest. So I have no sense of direction, so how can I put a direction? See, spin. I use a magnetic field, and I use the fact that these are fermions, neutron, and there is a spin, even nucleus has a spin. So I polarize the nucleus. For example, I take this direction, and I polarize a neutron. So there was a direction. Now, in a symmetric world, you would expect half of the time, if there are 100 electrons, that 50 would go up, 50 would go down. But they found they were all going down. To this day, we'll have to talk about which precision. The world still behaves with this painfully asymmetric way. For example, this bugs me. You know, when you think of new physics, you should think of the things that bug you, that you want to change. This bugs me. I like to paraphrase Einstein. I can imagine God being left-handed, but not an invalid. See, according to this picture, the world is just left-handed. You know, we define that left, okay? So I call this, say, direction where the electron goes, let me call this left. This will be right, okay? And it means, you know, that only left-handed electrons, those guys that we call left-handed, okay, know about the... I hate it. But that's the way it is. I'll come back to this. This is fundamental. Some years ago in the early 70s, this defined my path in physics, okay, Salam. And my first boss, Jogesh Pati in Maryland, where I did a postdoc, they suggested that maybe the world is not like this. But it actually could be more symmetric. But we don't see it, because it becomes symmetric at higher energies. Okay, I took it seriously, I've been following it ever since. The standard model is resisting to every attempt to make sense out of it that we personally feel to all of us. So it's purely left-handed. Electrons go down. These are things that I have to worry about. So in other words, the current, the V current, let me just write this, has this handedness, this chirality. I have to take into account that it's only left-handed. So the way we write it, it's only left-handed up quark acting, knowing about the left-handed down quark, and similarly a left-handed neutrino. Nobody ever saw a right-handed neutrino. As far as we know, there may not even exist. Very hard to believe because it has a mass, so we now suspect that it does exist. This is what we'll be discussing, okay? And this is, if you wish, can be written as U bar gamma mu 1 plus gamma 5 over 2 d, and the same n here. A warning. Some books write 1 minus gamma 5 here. In the notes I sent you, I write 1 minus gamma 5 here. They were written in collaboration with my younger collaborator at that time, Alejandra Melfo, took these notes and she changed plus gamma 5 into minus gamma 5. Now, does it matter? Can it matter? A reminder, how is gamma 5 defined?
Product of all times I times gamma.
Right, but its property, that comes later. What is it? Anti-commutes with gamma mu?
Yes.
Gamma 5 commutes with the generators, we'll discuss this. And gamma 5 square is 1. Notice today all of these things are said without any structure, okay? This is all digressions, okay? So the signs cannot matter. And you will run even in the books and even in the notes that appear every now and then, okay? The people say that the name it's called V minus A is because there is a minus sign, okay? It's not defined, you understand? So you have to somehow get used to the fact that someone will call it, because I can choose a gamma 5 which is minus your gamma 5, and one good thing would be that you and I have the same conventions. which is very hard if you already have different conventions, okay? So the advanced they will check what conventions you have and what conventions I have. When I was doing my PhD, my advisor at that time, Rabbi Mohapatra, was the product of the old school of Marshak, Sudarshan, and those guys. I wonder Weinberg at that time, those people, I think they were in between. They were using a different metric even. So imagine comparing calculation, it was terrible. And so these things are important. The thing that I will have to worry about seriously, that I have a propagator that somehow behaves crazily. I have the extra piece which goes 1 over mw squared. At some large k squared, I get a piece that goes to infinity when k goes to large. Infinity, by the way, like 0, are just ways of emphasizing, impressing each other. Right? There are no zeros in physics and there are no infinities, okay? I'll have to worry about that. This is what the standard model is all about. I have to make sure that I know how to write the theory. And it's challenging and it's interesting. And it's good to go back and see how it was done. I have to discuss electromagnetic and weak interaction on the same footing if I take it serious. But they're completely different. Right? Short range, long range. Parity conserving completely electrodynamics. This is completely parity breaking. And then I have this terrible thing that I don't have to deal about. This is going to take me to the peaks. And these things are going to take me to SU2 cross U1. I want to show you that it had to be SU2 cross U1. Okay. I'll stop here. Maybe one last question if you guys have.
Hierarchy of the masses.
Sorry?
The masses.
The ma?
Hierarchy of the masses.
Which are?
What is it? So it's between
Well, which? Tell me which. I want to.
the boson and the quark.
Remember, I didn't speak of quark masses. By the way, not only I won't say anything during this, I will not say anything about the hierarchy of the masses. I don't know why you ask me, because you may have asked me because you heard other people asking it, or it's something in you. Okay, this is what I will have to see when you guys ask me questions. Okay, there are two things that there is a sort of a dual way we live. We have one part which is ours, but we can't help reading about things, you know, and in order to belong to the common way of thinking about phenomena, we often cite other people. So one of the things that apparently you are alluding to, people say we should understand the hierarchy of masses. Should I? If someone enters here, there now, and it's much taller than the other person, then you and I would. If a person enters here and is 4 meters tall, you and I would worry about that, right? But you don't worry when you see two dogs which are widely different in size. You don't ever ask yourself why one dog is this small and the other is, like you almost. Well, why don't we worry about that? Forgive me if I take a few minutes on this fundamental question. Why do you think I don't worry about dogs, but I would worry about people? Well, I've learned that dogs are product of breeding of so many different species that